Okay, this is your Unit 10 Worksheet 5 homework help video. Reminder that this is not designed to replace the notes. It is designed to be an extra aid for those who want to practice a couple more with explanation, or maybe who have done all their homework and are wanting to check a couple just to make sure they did them right. Yeah, so if you have not watched the notes video, go ahead and pause this, go over there, watch that notes video, come back afterwards. Okay, we are going to be doing 2 in this homework help video, numbers 4 and 9. Reminder, your directions here, we're finding the domain restriction, what we call values of alpha and beta, in radians that create the partial graph as stated. That partial graph as stated just means whatever they have defined as what you're trying to find. So for example, in number 1, for part A, you'd be finding what domain restriction would give you just the inner loop here, B, the outer loop. Number 2, 1 petal centered on theta equals 0, that kind of thing. Okay, so to start us off here, we're looking at number 4, which is R equals 4 sine 3 theta, 1 petal in quadrant 1, okay, which gives us this graph here. A reminder from the notes video that what we know is that R equals 0 at that point. We don't actually know what our theta is because our theta could technically be anything if you think about your R theta coordinate points that we learned to graph in 10.1. The theta tells you kind of where you're oriented angle-wise around your polar coordinate plane. The R tells you how far you move, either in the direction of theta, if R is positive, or in the opposite direction from theta if R is negative. And so if R is 0, it means we haven't moved at all. And so I could be facing any angle measure right inside there and still have an R equals 0. So all we know is that R equals 0. What that tells us though is that if I'm wanting to define some domain restrictions that give me this 1 petal in quadrant 1 here, well then I can set this equation equal to 0, plugging in 0 for R here, and what I'll find are all the angles where my petal touches my pole there, right? Where the start and end of each of my petals. Okay, and so I'm going to go ahead and set my equation equal to 0. Okay, dividing 4 then over to the other side, we get that sine of 3 theta equals 0. And then if I take the inverse sine of both sides, which is something or at least you should know, you can use your triangles, your hand trick, just memorizing your unit circle, whatever method is you're going to do, we should know what angles give me a sine of 0. So think about that for a second. What angles give me a sine of 0? Okay, well that would be all your x-axis quadrantals, right? Where y equals 0, everywhere on your x-axis, which are 0, pi, 2 pi, etc. And in the negative direction, right? Negative pi, negative 2 pi, so on and so forth. Okay, so then what does theta equal? Well, if I divide 3 through, 0 divided by 3 is 0, pi divided by 3 is pi over 3, and 2 pi divided by 3 is 2 pi over 3, etc. Okay, well we only want the angles that give us that first quadrant angle, or sorry, first quadrant petal in here, which would be everything starting at 0 and going through to pi over 3. Okay? Okay, number 9 then. We've got our 2 minus 5 sine theta, and we're going to be trying to find an inner loop and an outer loop. Now, they did not provide us with a sketch on this one, so you have a couple of options. Either one, you could kind of mentally picture the sketch. You could actually graph it like we did, or we learned how to do back in Objective 3. We know that this is a negative sine graph, right? Negative 5 sine theta, so we know that our circles, like if I were to do a rough sketch here, our little loops are going to be down in the 3rd and 4th quadrant. So again, this is going to be a very rough sketch. All right, so we're looking at something kind of roughly like that. Because the 3rd and 4th quadrant is where sine is negative. The question then is, where are my restricted domains? Okay? So, same thing. Let's go ahead and set our equation equal to 0 because that's where we'd be touching our pole there. And then I can solve, subtracting the 2 to the other side. We'd have negative 2 equals negative 5 sine theta. Dividing the negative 5 would be 2/5 equals sine theta. And then that would be an angle measure you would not be expected to have memorized. And so you take your calculator and you do the inverse sine of both sides. Inverse sine of 2/5 we are told is about 0.4115, right? And so we'd be putting that down, okay? And then there are other angle measures where that would exist, right? So again, quick little rough sketch. Where else is sine positive besides in the first quadrant? Well, sine is also positive in the second quadrant. And so we're looking for how could I name that angle measure in my second quadrant that is related to that 0.4115, but we can't call that 0.4115. What could we call that? Okay, well that angle measure is pi, which is this left-hand side of the x-axis, minus 0.4115, right? Pi minus 0.4115, that angle, okay? And so then we're going to go ahead and do pi minus the 0.4115 angle, and we get around 2.730. Okay? So then my inner loop goes from 0.4115 to 2.730. And my outer loop then, my outer loop starts up again at that 2.730 where my inner loop ended and goes around continues the rotation all the way back around again to where we started, the 0.4115. But because the rotation's continuing, I can't actually call this 0.4115. Right? The rotation's continuing. This needs to be larger than that. And so I want to give this a coterminal angle name rather than 0.44 or 4115. We're going to add 2 pi to that angle. Because remember, back when we first learned coterminal angles, that tells me that this 0.4115, where that exists on my unit circle, if I add 2 pi to it, I've gone one full rotation around, I land in the exact same spot. And so we're going to call it that. So this is going to be 2 pi plus that 0.4115 angle, which is about 6.694. Oops. 2.730. Okay. Okay, if you have any other questions, send them your teacher's way.